This video will introduce the concept of a chemical equation and discuss exactly the different parts to it and how to interpret a chemical equation. The first thing you'll need to know is that a chemical equation is telling the story of what happened in the lab. So we can read these symbols and numbers and get a very solid understanding of what these chemicals underwent, what was mixed together, and what happened. So let's take a moment and compare two chemical equations. I have equation A and equation B. I'm going to go ahead and stop talking for a couple of minutes so that you can compare those two. So the first thing that you might notice when looking at these equations, these chemical equations, is that you have letters, you have numbers, and you have parentheses with letters in them as well. Some letters are capitals, some letters are lowercase. And you also might notice an arrow. Throughout this video, I'm going to teach you how to interpret every one of those numbers, letters, and symbols. But one of the things that I'm hoping that you recognized is that for equation A, looks like on one side of the equation, you have something that is written as CO2. And when you look on the other side of the arrow, you still have CO2. Your parentheses, the letters in the parentheses are different, but what you start with, the CO2, is what looks like is happening also on the other side of the arrow. Whereas in equation B, you have a group of letters, CO2, and then you have a plus sign with H2O on one side of the arrow, and on the other side of the arrow, you have a new arrangement or a different arrangement of C's, H's, O's, and also a plus. So in the first equation, it looks like what letters you start with are the same as what you end with. And when I say end with, that's at the other side of the arrow. Whereas in equation B, what's on one side of the arrow is differently arranged than on the other side. So let's discuss what that actually means. So if you take a look at these chemical equations and we look at physical changes versus chemical changes, and if you look at this equation a little closer, you're going to see that in physical changes, the sequence of letters before the arrow is identical to the sequence of letters after the arrow. So I have H2O on the left-hand side of the arrow, and then I have H2O on the right side. And that's the case for the second one also. N2 on the left side and N2 on the right side. So we can say that you start with the same chemical as you end. And remember, with physical changes, you always ask yourself, in any sort of change, did something new get created? And in this case, we see that H2O still continues to be H2O, so nothing new is created, and for that reason, it is a physical change. So you can always tell a physical change because the letter arrangement before or on the left side of the arrow is identical to the right side of the arrow. Now, in a chemical change, you'll notice for my first equation, which is this one right here, H2H2O plus O2, and then you have on the other side of the arrow 2H2O. We're using the same letters, but they're rearranged differently. And when we see something rearranged differently on the other side of the arrow, we say that that is a new substance. And so in this case, we have H2, 2H2, and then we add O2 to combine into something that's H2 2H2O. And you'll see that for this equation, I apologize, this should read this way. There we go. Get rid of that. That you have an H with a BR, but here you have an H with an O. Here you have an Na with an O and an H, but here you have still an Na, but it's with a BR. So they've kind of been scrambled up and rearranged, and we say that those are new substances. These are all examples of chemical equations. A chemical equation always has an arrow involved. So one of the things that you may have noticed is that there were parentheses. I'll go ahead and go back and show you where those parentheses were. Here's a set of parentheses, there's a set of parentheses here and there, and you see them everywhere. So what do these parentheses mean? These parentheses tell us the state of matter of each chemical. So if you have the chemical written in its symbols, for example, H2O, and you see the letter L, L stands for liquid. So that water was in liquid form. If the water were in solid form, H2O as a solid, I would write an S, and that should be solid. There we go. We also have G representing gas. The one that you may not have seen before is AQ, which stands for aqueous, and that means that it is a chemical that is dissolved in water. All right? So as soon as anything's dissolved in water, we simply write AQ. So let's give it a try. Let's see if you can interpret what the state of matter of each chemical is and what you would expect to see. So here I have a long chemical equation, and I would like you to visualize what you would see on the lab table. Would you see beakers of liquids? Would you see beakers of solids? Would you see beakers of gases, or I should say balloons of gases? And after this, these chemicals come together, what would you expect to see? So if you looked at this chemical and you notice that it says a solid, probably you're going to find a solid on your table. That means on your lab table there will be a beaker with some solid powder. Here I notice that I have an aqueous solution, and so very likely for this one I'm going to see, draw an Erlenmeyer flask with a solution of HCl. So I can immediately know which chemical is which just based on the state of matter. When I mix these two together, if I were to pour this into that, it's going to tell me that these three new chemicals are going to be produced. So what would I expect to see? If you said you're going to expect to see bubbles, you're absolutely correctly. Why are you going to expect to see bubbles? Because G stands for gas. That means that a gas is going to be produced. So when you look at those bubbles, you know exactly what that bubble contains. It contains a chemical CO2. For the H2O and the NaCl, these are both liquid forms. Remember, aqueous means it's dissolved in water, and we won't be able to tell the difference between these two because they're both more or less liquids combined together. So just by looking at a chemical equation, I was able to take a look and understand a lot. I knew I started with a solid and a solution. When I combined them together, I knew that I was going to get a gas, and that gas was going to be CO2. So it tells the story of what's happening in the lab. So let's take a moment to actually break down a chemical equation. So we're going to be using this chemical equation that I have right up here, and I'm going to discuss the type of elements you're going to find, which elements are bonded together and how. I'm going to identify what goes in and comes out of a reaction and how much, and the phases of each of these reactions. So get your notes ready and let's get started. So first of all, what I'm going to do is look at the chemical reactions, and I'm going to start looking for capital letters, okay? So a capital C, in this case a capital H, and a capital O. Now, remember, we only have 27 letters in the alphabet, so at one point we have more than 27 elements. We ran out of letters. So a C represents carbon, whereas a C with a lowercase a will represent calcium, where then a C with a lowercase s is going to represent cesium. So if you see a lowercase letter, just know that it's because we ran out of the alphabet and we're now using the letters, lowercase letters, to help us figure out which chemical it is. So in this case, how many different atoms do I see? Well, I look for all the capital letters that I can find. I have a C over here. It looks like I have an H over here. And I have an O over here. Now, I'll give you a trick. You never have to look on this side of the equation, on the right side, because the letters are just rearranged. So all you need to do is look on the left side to see how many different types of atoms I have. Or we can say elements. In this case, I have 3 different atoms. All right, now let's try the next one. Now we're going to identify the compounds. One of the things, remember, that we talked about in class were compounds. And we were saying that elements are essentially, we'll use these circles here, the same atom existing in the same place. And then we said elements are where you have, compounds are where you have different atoms attached to each other. So this is an element because we have the same type of atom. They are not bonded, and you can say that they're not bonded, and this one is a compound because we have two or more different types of atoms, and they are attached to each other. So in this case, how do we identify which is a compound? And that is easily done in that if the letters are written together, you have a compound. So C and an H are written together with no plus sign in between. This is a compound. And I'm looking for at least 2 different letters. So I have C3H8 being a compound. Is O2 a compound? No, because I only have one type of element. I only have the O. How about H2O? They're written together, and I have 2 different letters. So for that reason, H2O, and I can put the 4 here, H2O is a compound. How about this one, 3CO2? Do I have 2 or more different letters written together without a plus sign in between? The answer is yes, that's a compound. Okay, so what we can do is we can actually draw what that looks like. So I'll make mine a little bit easier. It makes no difference how you draw it. That tells me that I have this number, 3 carbons. Let me make this a little larger. Because I have that little number 3 here, tells me that I have 3 carbons. I'll put a C for that. And how many hydrogens is it that I'm going to have? I'm going to have 8. So I'll go 1, 2, 3, 4, 5, 6, 7, 8. And at this point, it makes no difference how you draw these circles because you just want to represent that they are clustered together. Okay? Then let's do H2O. I have 1 O. The reason I know that it's 1 is if I don't have a number here, I know that it's 1. And I have an H here and an H here. I have 2 H's. Again, it makes no difference how you draw those. We'll deal with the big numbers in just a little bit. I have C here and then 2 O's. Remember, I'm ignoring the big numbers, but I'm just looking at these small numbers. This tells me I have 2 hydrogens and 1 oxygen. Because there's no number here by the carbon, I'm going to assume I have 1 carbon and 2 oxygens. All right, now we call anything that goes into a chemical reaction the reactants. So everything on the left-hand side of the equation is called a reactant because that is going to react. And everything on the right-hand side of the equation is going to be called a product. That's what you're left with. This is the end result. This is what you produce. So in this case, our reactants are C3 and H8 and 5O2. Our products are 4H2O and 3CO2. So in this here, we've answered our question already before, but how many carbons are contained in C3H8? And if you said that there were 3 carbons, you're correct. For H8, we said that there are 8 hydrogens. C stands for carbon, H stands for hydrogen, and that's okay if you don't know that right now. What is the difference between a chemical symbol and a chemical formula? Now, the chemical symbol is the letter given in the periodic table. So the symbol for carbon, the chemical symbol, is C. The chemical symbol for calcium is Ca. The chemical symbol for hydrogen is H. So that's a chemical symbol. When you write, when these chemicals are bonded, symbol, there we go. When these chemicals are bonded together, then you create something that is a chemical formula. So, for example, C3H8 is chemical symbols written together to show bonding. So in this case, this is a chemical formula, C3H8. H2O is also a chemical formula because it tells me that I have 2 hydrogens bonded with an oxygen, the chemical formula, where a chemical symbol is just the individual element that you're using. Does this diagram represent a chemical or physical change? What evidence supports your claim? So remember, you're looking at the reactants, that's the left-hand side of the equation, and comparing it to the products, the right side of the equation. Are the letters arranged the same, or are they arranged differently? In this case, I see that I start with C3H8, but I no longer see C3H8 on the right-hand side of the equation, so I know that this is a chemical change. Something new has been made. So now comes the next piece. How many molecules of H2O are produced? And this is where you get that information. The big number, and we call that a coefficient. Coefficient represents the number of molecules or compounds. we can use these words equally. Okay? So in this case, because I have the number 4 for H2O, I know I have 4 molecules of H2O. So that would mean, if I were to draw that out, I have 1, 2, 3, and 4. Okay? So that means 4 molecules of H2O are made. How many of molecules of O2 are used? I would then say 5. 5 molecules. Now you'll notice that the molecules of O2 means you have 2 O's bonded together thanks to that little 2. So just a reminder, in this case, this tells you how many are bonded to each other. And this tells you how many groups of these you have. All right? And what's the state of matter you start with and you end with? Well, it looks like I am starting with a gas here, and then I have a liquid forming, and also a gas. So I start with gas, and I end with gas and a liquid. So there's a lot going on with what I just said. So what we're going to be doing is we're going to wrap it up and just summarize. So let's start with reactants. What are the reactants in this chemical equation? I have CH4 and 2O2. If I were to draw these, I would draw one C with 4 H's, and then I would draw 2 sets of O2. So I know that I have just one of these because it is empty. There's nothing there, so we assume 1. I know that I have 1 carbon because I have nothing written here, so I assume 1 with 4 hydrogens. For this one here, I have 2 O's bonded together thanks to this number 2, and it tells me I have 2 sets. My products, remember reactants are on the left side, products are on the right side, are CO2 and 2H2O. So if I were to draw that, I have a C with 2 O's, and then I have an O with 2 H's and another set of O with 2 H's. How do I know that I have 2 sets? Is because of this. So my description would be 1 molecule or compound of CH4 gas, don't forget your state of matter, mixes with 2 molecules of O2 gas to form 1 molecule of CO2 gas and 2 molecules of H2O liquid. I take a look. Is my arrangement the same from beginning to end? It is not. I have a new arrangement, and so it is a chemical change.